Reconstructing an examiner. Occasionally, paleontologists dig up a small fossilized bone and proceed to reconstruct the shape of an extinct animal. A similar activity is possible in regard to examiners. The question set taking the place of the fossil bone. A good examination question is not just a shapeness affair. It should contain some interesting design or some surprising result. Such questions are by no means easy to make up. Accordingly, an examiner who is doing research work will usually be on the lookout for some result that he can use in examination questions. Often, in very advanced work, some small pieces of algebraic manipulation occurs, which can be detached from its context and set as a problem. That's why some of the problem is completely detached from the context. For example, some years ago, students brought me the following question, which had been set in an examination paper and which they found hard to solve, or at any rare to solve in a satisfying manner. Proof that if AC minus B square divided by A minus 2B plus C equal BD minus C square divided by B minus 2C plus D. It is assumed that the B and C are unequal. The text does not discuss this point, as it is not relevant to the main theme. What suggested the question to the examiner? That's interesting. Then the fraction just given are both equal to AD minus BC divided by A minus B minus C plus D. This question has very definite form, and obviously to hammer it out by lengthy and shapeness calculations while verifying the result would bring one no nearer to the heart of the question. What interested me most was the question: how did the examiner come to think of this question? The pattern of the question induces the following aspect. AC minus B square equals 0 is the condition for the three equations, for the three quantities A, B, C to be in geometrical progressions. Yes, the numerator of the first fraction contains AC minus B square. A similar expression occurs in the numerator of the second fraction. Down below we have an expression A minus 2B plus C and B minus 2C plus D, which are associated with arithmetic progressions A minus 2B plus C equals 0 being the condition for A, B, C to be in AP. Again, there is a kind of the rule by which the denominator could be derived from the numerators. In the third fraction, for example, we have A and D multiplied on top, added below. For example, the numerator contains AD, the denominator or A plus D. The negative terms are similarly related. On top, we have minus BC, down below minus open parentheses B plus C, close parentheses. This rule applies equally well to the first two fractions. In the first fraction, for instance, minus B square is minus BB, and we find minus open parentheses B plus B, close parentheses, that is minus 2B below it. To prevent a problem so knit together is almost impossible. One does not invent such things, one stumbles upon them. I was certain that the examiner had been finding the condition for something, and these fractions had arisen in the course of the work. That is why this is not in harmony. It's very artificial, yeah. The way to begin the problem was fairly obvious: to bring in a new symbol k for the value of the fractions. The problem then can be stated as follows. If AC minus B squared divided by A minus 2B plus C equal K 1. And BC minus C squared divided by B minus 2C plus D equal K Roman 2. Prove AD minus BC divided by A minus B minus C plus D equal K Roman 3. To bring in such a simple K is routine procedure when dealing with the equality of the several fractions. See, for example, Hall and Knight, Higher Algebra, Chapter 1. What to do next was not at all obvious to me. I tried various methods which, though they led to proof, did not satisfy me. I continued to think about this question in odd moments, and about a week later hit on the following approach. Equation Roman 1 can be put in the form AC minus K open parentheses A plus C close parentheses equal B squared minus 2BK. Both sides of this equation are now crying out for an extra term K squared to complete their pattern. This will complete the square. Aha, this is complete the square. In Japanese, it's called heihou kansei. On the right hand side, giving a open parentheses B minus K close parentheses squared, and give her open parentheses A minus K times open parentheses C minus K on the left. So, open parentheses A minus K times open parentheses C minus K equal open parentheses B minus K squared. That is to say, equation Roman 1 expresses the fact that A minus K, B minus K, C minus K are in GP. Now we have the whole thing. Equation Roman 2 shows that B minus K, C minus K, D minus K are in GP. So A minus K, B minus K, C minus K, D minus K are in geometrical progressions. Wow! But if we multiply together the first and fourth terms of the GP, the result equals the product of the second and third terms. Let the GP be large A, large AR, large AR square, large AR cubed, then large A times large AR cubed, equal large AR times large AR squared. So we have a So we have a open parentheses A minus K times open parentheses D minus K equal open parentheses B minus K times open parentheses C minus K. If we multiply this out, cancel K squared, and solve the resulting linear equation for K, equation Roman 3 results. Our conclusion, therefore, is that the examiner's researches had led him on some occasion to pose the questions. Wow! What is the condition that four numbers A, B, C, D must satisfy if by subtracting the same number from each of them, a geometrical progression can be obtained? The moral of this is not conformed to examination questions. It is meant to support the thesis. Where there is a pattern, there is a significance. If on mathematical work of any kind we find that the certain striking pattern recurs, it is always suggested that we should investigate why it occurs. It is bound to have some meaning which we can grasp as an idea rather than as a collection of symbols. It is extremely unsatisfactory to discover a theorem and only be able to prove it by shapeless calculations. By shapeless calculations. It means that we do not understand what we have discovered. Right. To find the significance of the algebraic formula may take a long time. There are usually so many possible methods of the attack, and no way of telling which is the true ones. I find that in dealing with such problems, my brain has a delayed actions. At first, I can make nothing of the question, a delay, or a week or a month later, an inspiration comes. If the students are required to solve such a problem within the 3 hours, that is under the examination conditions, a considerable element of the luck is brought in. The usual way of overcoming this difficulty is to put in front of the problem a piece of bookwork or some simpler problems that we will start the mind working in the correct directions.